Hello students, my name is Sumit Sagar Hota. Uh, I am a PML PhD scholar, IIT Palakkad. Uh, Today we will discuss uh, week 4 of the live discussion section, in which we will cover lecture 16 to lecture 20 by Professor Ashok Desai, IIT Kanpur, of the subject Turbulent Combustion Theory and Modeling. Sorry for the slight delay due to network interruptions. Okay, in this section I will discuss some of the MCQ questions as well as some problems. Okay, so okay, so let's start the section. And the problems are taken from this book. You can see this book, An Introduction to Combustion Concept and Application, third edition, 2017, McGrail. Okay. So let's come to the MCQ part. Okay, what is the primary difference between the laminar premixed and non-premixed flames? Okay, so in this section I think it is related to your laminar premixed and laminar non-premixed flames. Okay, just I think that's the section. So just quickly go through these problems, MCQs. Okay, what is the primary difference between the laminar premixed and non-premixed flames? Options are temperature distribution, fuel and oxidizer are mixed before combustion, flame stability, and none of the above. Okay, so how we will differentiate the premixed and non-premixed flame? Okay, the answer is very simple. That is the fuel and oxidizer are mixed before the combustion. Okay. Yes, you can ask the question, Ramesh.
In pre-mixed also before combustion it has to be mixed. Now both non-pre-mixed also before combustion it has to be mixed.
Um, no, actually, uh, you see, okay, the confusion arises. Okay. Mm, 1 second. Ah, so in okay, okay. First, I tell you what is non-premix. Non-premix means, for example, here one. Okay. Okay, here one nozzle is there. Okay, two nozzles are there. Here the oil is going. Okay, and here your air is going. Okay, similarly here also air is going. Okay, and fuel having some different velocity, maybe v1, air having some different velocity, maybe v2. Okay, so we have to apply some, maybe here, maybe in this location we have to apply some spark. Okay, okay, maybe the spark for maybe 0.5 second to 1 second maybe. Okay, so because of that there will be a flame. Okay, Okay, so this is what the case. Okay, so now what it's going on that air and fuel are not mixing together. Okay, air and fuel are not directly mixing together. Okay, when they are mixing at the point where that combustion is taking place. Okay, now this is what called your diffusion flame. Okay, or non premixed flame. Okay, now one more case I am telling. Okay, here we can take the example of one what you called Bunsen burner. Okay, mostly in chemistry equipments you just see the Bunsen burner. Okay, that example is also the case of pre-mixed. Okay, one more also type you can expect is that uh, here uh, here the air supply is there. Okay, okay, and here the fuel supply is there. Okay, it's a kind of burner. Okay, so here air supply, here fuel supply is there. Okay, and here there will be the flame. And make it shape little less. Now here there will be flame. Okay, so here what's going on? Here air and fuel are mixing together here. Okay, here mixing is taking place. Okay, then here you are applying some spark. Okay, and then there is flame formation is there. Okay, so this is your pre-mixed. This is very similar. Okay, you may confuse, but yeah, this is what the slight difference between them. Okay, and very well example in your chemistry lab. One more example you can take is that, for example, one burner is there, like your our our home these stoves will be there. Okay,
Yeah.
so there okay, that is also one example of pre-mixed flame. Okay, why? Because this kind of structure is there, na? And yeah, and some holes will be there here. So here our whatever LPG gas will be there, from here the flames will be there. Okay, here. Okay. Stop. So what's here? Here it's taking the our atmospheric air as the oxidizer. Okay, so when air and fuel are mixing together in the atmosphere. Okay, so when you also know that somebody in the films also, we can see somebody turn on the air for some time, and then somebody take the lighter and turn on, then the explosion is there. Okay, that means what? That means up to that point the spark actually, at that point the spark means the fuel just reaches. That's the reason this explosion is there. Okay, so that means air and the fuel mix together very well. Okay, in the stoichiometric ratio, and when we supply the spark, there is a burning is taking place. Okay, that's one example I just taken. Okay, the stove is also a very good example of your pre-mixed flame. Okay, so when air and in one word, if I or one line if I can tell, when air and fuel just mix together, and then the spark is applied to burn the to burn the fuel, then it's called pre-mixed. Okay, when air and fuel are going in a different path. Okay, maybe they are not mixed, they are not mixed before the before the combustion. The both are not mixed. Okay, not, for example, you see now here in pre-mixed, what I can control now, we can control the equivalence ratio. Okay, no, I even know I want a little lean mixture. Okay, so I can take, let it be phi equal to 1, sorry, phi less than 1, phi greater than 1. Okay, so these kinds of cases can be possible in case of your pre-mixed flame, but same thing cannot be possible in your diffusion, cannot be possible in your diffusion flame, because you are supplying some definite amount of air and you are supplying some different amount of fuel. Okay, and because of that, outside the combustor, they are mixing together, and they are all these means because of spark, that combustion is taking place. Okay, so their mixing is not the major importance. Okay, so the fuel having very less ignition means ignition, auto ignition temperature, those kind of fuels can be mostly burned in pre-mixed flames. Okay, uh, so that's what the example. Okay, so that means what, LPG, all these things we are burning in the pre-mixed flame. Okay, very highly for example, if you can see methane flames. Okay, methane flames is you can use it in diffusion flames nowadays. You can see in other different countries like China, all these countries, they are using as a rocket fuel. Okay, so that's what the means basic difference between the pre-mixed and non-pre-mixed. Okay, then now we are this is pre-mixed and means non-pre-mixed, and depending upon the Reynolds number, you can take it as your laminar flame, turbulent flame. Depending upon the Reynolds number, you can get. So that's what the whole story. I think I expect this thing should be covered in your lectures. I don't know. So anyway, I think your basic understanding now will be, I think, clear. Okay.
Yeah, thank you, sir. It's clear.
Okay. So now next question. Okay, now next question. Mm. In a laminar premixed flame, combustion occurs. Okay, means actually all the 6 questions whatever I taken, all are similar. Okay, just different way of asking the question. So I just quickly go through all these I think questions. In laminar premixed flame, the simultaneously mixing of fuel and oxidizer occur. Okay, so that's what the case here. Simultaneous mixing. Okay. Which of the following is a characteristics of laminar premixed flame? Yeah. So actually, I already told this because whichever fuel having very high low autoignition temperature can be burned here. Okay, that means faster burning can be occurring. Faster burning speed can be occurred in what, more in the premixed flame. Okay, as compared to the non-premixed. Okay, means so, some interruptions are there. So start the class. Okay. So burning speed. Okay. Okay. So my next question. Okay, what's this question is means the burning in laminar pre-mixed flame is very higher as compared to the laminar non-pre-mixed flame. Okay. We go to next question. Which of the following is a characteristics of laminar pre-mixed flame? Same questions. Okay, just in a different ways. It's asking. Okay. Fourth question is in a non-pre-mixed flame, combustion occurs in which of the method? In a non-premixed flame, combustion occurs in dash. Non-premixed means oxidizer and fuel are completely mixed. Okay. So that means that the fuel and how you know fuel and oxidizer are completely mixed in non-premix. That's the beauty. So that's the means difficulty in your diffusion flames. Okay. So you have to supply the spark in such a way that your fuel and oxidizers are mixed. If it is not, if for example you provide the spark but your only fuel is there but there is no oxidizer in the means atmosphere. For example, you are doing the experiment in a inert atmosphere, maybe argon is the fuel. In one combustion chamber is there argon is the fuel or nitrogen is the fuel. Means nitrogen is the means inert environment you are giving and you are supplying the diffusion fuel and there is no oxidizer and you provided the spark. That means there is no use of spark, there is no kind of no combustion occurs. Okay. So when the fuel and the oxidizer completely mixed, then only you have to supply the spark so that there will be a combustion occurs in the diffusion flame. So that is the difficulty in diffusion flame as compared to your or non-premixed flame as compared to your premixed. Premixed directly everything is just mixed and then directly it will come and then because of spark it is just ignited. So so modeling the fuel means non-premixed is difficult as compared to your premixed flame. So that's not the thing. But this is advantageous for means for high auto ignition temperature based flames. So yeah. So which of the following is the characteristics of non-premixed flame? Okay. This burning speed I think already I discussed here. Okay, same thing again. It's there. Okay. Okay. So The non-premixed flame having slower burning speed compared to the premixed. Okay. In a non-premixed flame, combustion is typically what? Okay, I already told combustion non-premixed means flame is also called as diffusion control or diffusion flame. Also, we can call. I already written the answer. Okay. Also called as because of the diffusion of fuel and oxidizer, this flame will propagate. So that's what the case here. Now we come to the numerical question part. We'll solve some of the questions from chapter 8, and I think most of the questions are from chapter 8. Okay, and some of the questions, one question I just solved for chapter 9. I think maybe next lectures, I think your full laminar premixed and non-premixed will be covered, and then I will solve some of the problems of chapter 9 also. Okay, so that's what the plan. Chapter 8 should be I think will be completed. Okay, consider the outward propagation of a spherical laminar flame into an infinite medium of unbound gas. Okay, assuming SL, TU and TB are all the constant, determine the expression for radial velocity of the flame front for a fixed coordinate system with its origin at the center of the sphere with mass conservation for an integral control volume. Okay. So basically it's already written spherical laminar flame into an infinite medium of unbound gas. Okay, let's solve it. It's a very simple question. What is given? Outward propagation of spherical laminar flame. What we need to find? drf by dt is equal to v equal to radial velocity. We can represent it. They ask determine the expression for the radial velocity. We are related. So what is the assumptions? spherical symmetry. What does it mean? Because the flame is symmetric. Okay, sphere is symmetry everywhere, means this is sphere is symmetric, but for flame we cannot tell that it's symmetry, so that's the reason we are assuming it as purely symmetric everywhere. This is your flame front. What is m dot in? Mass flow rate into the control volume, which is equal to rho AB. We know m dot is equal to rho AB from the continuity equation. Here velocity is the laminar speed, area is the flow area, okay, which is the sphere, and sphere's area formula is 4 pi rf square. Okay, f for fuel I am telling. Okay, u for unburned and b for burned. So now what is mb? Bond 1 rho b. What is the volume of the sphere? 4 by 3 pi r cube. Okay, let's apply conservation of mass. dmb by dt is equal to m dot in minus m dot out. There is only material into the control volume. There is no out as given in the question, so m dot out equal to 0. Okay, so only that is m dot in will be there, and we know what is m dot in. Okay, so I have to just solve it and get the answer. So d by dt of rho b 4 by 3 pi rfq is equal to rho u sl 4 pi rf square. Okay, so now 4 get cancelled, pi get cancelled. Just take the derivative. 1 by 3 rho b 3 rf square drf by dt is equal to rho u sl rf square. Okay, 3 get cancelled, so drf by dt is equal to your radial velocity is equal to rho u by rho b into sl. Okay, so all this hard work of doing this question is directly in your exam. They will ask all this situation. There is one spherical laminar flame is there. Okay, then they will give what is rho u, the value of rho u, the value of rho b, and the value of sl. Then they will tell you find the radial velocity. If this expression nowhere you can find out. Okay, in book also it may not be there. If you derive this thing previously, then at least in once I think 1 minute you can have the answer. And if in your exam if you do this derivation, it will take next 5 to 10 minutes and wastage of time. Okay, so directly remember this expression. That's the best thing of doing it. Okay, so what is the condition? Some b r is always greater than sl. Okay, this is one condition you should remember, and rho u always greater than rho b. Okay, some of the conditions they may ask also. The radial velocity, whatever it's there, is always greater than your laminar flame speed. Okay, why? Because rho u will be rho u greater than rho v. Okay, after burning, obviously the density will be less than when before burning the hot fuel. Okay. That's all. Okay. So derivation is very simple to remember. So if you know the procedure, and I think if you know this formula, I think most of the question I think you can answer. Okay. So some proof they are asking. This is also a very good formula. This proves all these things. You can expect some of the in your mains or other some exams. This kind of proofs you can expect, but this formula you will expect in your some of the problems you can expect in your MCQ questions. Okay, in NPTEL. Prove that the simplified thermodynamic employed in the chapter 8 flame speed theory delta S equal to nu plus 1 Cp Tb minus Tu. Okay. So whatever chapter 8 you don't care, you just remember what's it written, simple thermodynamic. Okay, what to show? So delta SC is equal to nu plus 1 Cp Tb minus Tu. Okay. So what are the assumptions I can take? Okay. Now in this question nothing is given, only written simple thermodynamic. Okay, this is actually a confusing question. Simple thermodynamic, you don't know what is simple thermodynamic. If you don't know, then it's very difficult to answer this kind of question. Okay, so how to approach this kind of question is, always remember when this kind of questions are there, we can approach this question by assuming adiabatic flame. Okay, Cp of that's the reason I written Cp of the species are constant and equal. Okay, if you know very well that once we take constant value volume condition, then constant pressure condition, constant specific heat condition, I actually solved one question and then find out the adiabatic flame and assume it as a adiabatic flame, then I find out the heat of means whatever I just compare the whatever enthalpy of the product or enthalpy of reaction, or we find out the heat of the reaction. Okay, so that's what the all things now we have to again do. Okay, so just assume adiabatic flame. HP is equal to HR. Okay, so HP is equal to HR, so that means what is HP? Okay, you know HP, you have to first of all write down the basic expression for a what reaction, which is 1 kg of fuel, okay, plus new kg of oxidizer gives rise to 1 plus new kg of product. Okay, so this is what the basic expression you always take. Okay, while solving this kind of question, that means nu plus 1 times of HP. HP means your per mass basis. Okay, and mass is your 1 plus nu or nu plus 1 whatever. Okay, enthalpy of the product Okay, then enthalpy of the fuel into 1, always that is same value, nu times enthalpy of the oxidizer. Okay, so that's what the plan. P is your product, F is your fuel, OX is your oxidizer. Okay. Now what I will do, now we have to substitute in this. Okay, so you know H is equal to enthalpy of formation plus what? What is it? What is enthalpy? Enthalpy always is the sum of what? Enthalpy of formation plus sensible enthalpy. Okay, so HF is your H dot F is your enthalpy of formation. Then CPT minus TREF is your what? Sensible enthalpy. Okay. So now we just have to convert into that form. Okay, which is just replace H with H dot F plus CPT minus TREF. Okay. H0 means H0F means it is in standard condition. Okay, standard means 298 Kelvin and 1 atmospheric pressure. Okay, so Cp into Tb minus TREF. Okay, product is always bond. Okay. Product is equal to H dot of F plus Cp Tu minus TREF. Okay, fuel plus mu times H dot F Cp Tu minus TREF. Of oxidizer. Okay, now what we will do, we just do some rearrangement. Okay, to find out the what. Okay, so now we find out delta SC. Okay, by rearranging. If it's minus of delta SC, we will get to know nu plus 1 Tu minus TREF minus nu plus 1 into Cp Tb minus TREF. Okay, so that's not the case. Again, if you do some rearrangement, we just get to notice that when you consider delta SC, we just remove all the whatever the at the H dot F. That means delta SC is how it's made with by taking all the delta H dot F into the left hand side. Okay, so that's what the one trick you get to know. Okay, because delta SC enthalpy of combustion can only be calculated on the uh, standard temperature condition. Okay, that's the beauty of the enthalpy of combustion delta SC. Okay, so that's the reason why So which way just take all, this is all the whatever it's there. Okay, you can see all TU, TRM, all these things. This is your what? Sensible part. Okay, sensible enthalpy. What's your sensible temperature rise? Sensible temperature change you can write. Okay, so that's what the beauty. Okay? So this is your enthalpy of combustion. You know the definition. It's always calculated based on the enthalpy of formations only. Okay, so delta S is equal to nu plus 1 into TB minus T. Okay, if you again rearrange it, this is your answer. Some of the steps I removed, you just, that is your homework, you just see how it's done. Okay, that way you can get to know what exactly delta HC is. Okay, so just quickly go to the next question.
So CP is missing.
Oh, CP I forgot. Answer. Yeah, correct. Okay. It's correct. So actually this formula is very important. Okay, this formula is very important. Mostly this from this formula directly the questions can be asked. Okay, so this is very basic formula. So all these new CP, TB and TE will be given, then they will ask you what is the enthalpy of combustion. Okay, so this kind of question can be very easily asked. Okay, so when you know the proofs in your exam also, for example, you forgot, then you can in your exam also you can do the proofs and get the answer. So because directly if you remember the formula, it's very difficult. If the for example change the condition that okay, find out the enthalpy of combustion. That may be your homework, you can take. Okay, for example they will ask, okay, instead of simplify thermodynamics, take constant volume condition. Okay, take the constant volume condition and then find out your enthalpy of combustion. Okay, this kind of question will be asked. Okay, so there this CP won't be there. Okay, so there all this expression, everything can be calculated based on your constant volume. How we calculate initially the adiabatic flame temperature with constant volume condition, that you have to check. Okay, and there you have to know how to calculate your delta SC. Okay, and from there the other expression of delta SC will come in terms of CV. Okay, so that's also that's also obviously you should derive it and make it ready and remember it, so that in your exam it will be helpful. Okay, don't derive in your exam, so wastage of time. Okay, so just quickly go to one very simple problem. Okay, this kind of I think question you can expect in your exam. It's a very simple problem. Okay, you can see, and a pre-mixed propane, that means in chapter 8 mostly we cover all the pre-mixed part. Okay, and because non pre-mixed part is not yet covered. In week 5 I think, yeah, week 5 lectures, it's covered all the non pre-mixed part also. Then I will also again solve some of the more questions on the non pre-mixed in the next lectures. Okay, so now in this pre-mixed propane air mixture emerges from a round nozzle with a uniform velocity. Okay, we have the velocity, exit velocity of what, 75 centimeter per second. Then the laminar speed of the propane air mixture is 35 centimeter per second. Okay, so laminar speed is 35 centimeter per second. Okay, so a flame is lit at the whatever, what is the cone angle, means what is a flame is lit at the nozzle exit means whatever I am writing here exit velocity, that's what it's actually telling. Okay, so what are the velocity is there is 75 centimeter per second, that is the exit velocity. Okay, so what is the fuel? Propane. So what we need to find out the cone angle of this flame. Right principle determines the cone angle. Okay, what is the principle for that cone angle also you need to find out. Okay, principle obviously you know trigonometric principle we are using. Okay, trigonometric methods. Okay, so principle is not a big thing. Oh, I don't think so principle they will ask, so they will only ask you the what is the flame angle or flame cone angle with the assumptions. Uniform velocity profile at the nozzle exit. It's never possible in practical situation. At the exit anyway, it's impossible to get uniform velocity profile because there will be some non-uniformity because of because it's when it's open to the atmosphere, because some turbulence maybe it occurs. Okay, okay. Although it's a laminar flame, that may be some turbulence or some other, because of some other factors, density difference. This cannot be uniform always at the exactly near the exit. Okay, so yeah, so so, so very simple formula. Just in one line we can write down your alpha is equal to flame. This is very important formula. This I think 99.5% any of the combustion means exam, if you go anywhere you'll go, this question is very common. Everywhere this question can be asked. Okay, SL by V. Okay. This derivation, all this thing I think already there in your I think lectures. You can check that. 75 by 25. That is some 27 point. Remember this is in degree. Okay, directly the answer will be in degree. Okay, this simple question can be asked in your lecture. Very simple. So next is yeah, this is actually a lengthy question. We'll quickly go through this question. Some equation they are telling. This is like slightly lengthy question. Okay, but this is a very good, because 2 or 3 questions can be combined together to make this kind of question. Okay, so yeah, because in this question I will tell you what short question they can ask. Okay, so just quickly write down what is the things given. This question looking difficult, but it's not that much difficult. Some equation 8.33, I will tell what is equation 8.33. Then fuel given, endolene. Okay, endolene is very confusing name, same as gasoline. Okay. Okay, so what do you need to find? SL. Okay. laminar flame speed we need to find out. Okay. So come to solution. What is equation 8.33 is Met Galchis and Keck's correlation for laminar speed. Okay. In your exam, directly in one word they will tell take Met-Galchis and Keck's correlation and find out the laminar flame speed. Over. Okay. They'll give you the whatever the data it is required. Okay. So and they tell you directly find out the laminar flame speed. If you don't know what is this correlation, then obviously you cannot do this kind of question. Okay. So SL is equal to SL is your laminar flame speed. Okay. REF means reference. T means actual temperature by reference temperature to the power gamma is some constant. P is your pressure. REF is your reference pressure to the power beta is some constant into 1 minus 2.1 y dilution. How much air and fuel or oxidizer and fuel are mixed. Okay, that determines by y dilution. Okay, and one more. What is the formula for SLREF? These formulas, whatever I am writing, very important. You should remember all these formulas. Okay, 5 minus 5m to square. Okay, so but obviously TREF is equal to 298 Kelvin and PREF we are assuming as 1 atmospheric. Then how we find out gamma on this thing? Okay. Your gamma is equal to 2.16 minus 0.8 into 5 minus 1. Okay, so you know very well here nothing told about the phi. Okay, so we assume phi equal to 1. So I think it's given phi equal to 1. Okay. It's given phi equal to 1 and t equal to 560 Kelvin, p equal to given. Okay, all the data are given. So phi equal to 1 given, that means I just substitute in this formula, which is equal to 2.16 and your beta will be minus 0.16 plus 0.22 5 minus 1, so minus 0.16. 99% of case this 5 given 1. Okay, so obviously gamma and beta will be 2.16 and minus 0.16. Okay, so that's what the case. So for one table you will be given. Okay, they have to give you the values. For indolene I will tell you where is the table 8.3 page 285 of your book SR10. If you see, you will find out this table. 5m is equal to 1.13 bm 27.58 centimeter per second. B2 is equal to minus 78.34 centimeter per second. This value they should give. 5m, bm and b2 they should give these values. Okay, in your exam. Okay, so now we are all set to find out SL REF, the reference laminar flame speed. Okay, so directly we substitute where is the bm plus b2 5 minus 5m whole square. Okay, 27.58 plus minus 78.34 into 1 minus 1.13. Okay, SLREF is equal to 26.26 centimeter per second. So now you have the SLREF. Now you have to find out the SL. Okay, the laminar flame speed. So just SL, write down. Okay. In your SL formula, you just see SLREF T by TREF P by PREF 1 minus 2.1 into Y dilation. Okay. So all these T value 560 Kelvin, P value 13.4 atmospheric. All these values are given. Okay. Then the exponents gamma and beta all are also given. We just find out 2.16 and minus 0.16. Okay, now we are all set. We just have to substitute and find out SL. Okay, which is 26.26 560 by 298 2.16 13.4 by 1 minus 0.16 1 minus 2.10. Okay, what is why this is 0? So y dilation equal to 0. Right? What is y dilation? We have to first of all know. Okay, y dilation is equal to x by 100. Okay. If x% by mass of exhaust gas recirculation okay, so here in this question there is nothing told about the how much your exhaust gas is recirculated. Okay, so that's why you assume mostly if there nothing is given, we assume y dilation is equal to what? Y dilation equal to 0. Okay, so that's what the case here. Now this part is here, but this part is 0. So now don't write all this confusion will be there. So SL is equal to 68.57 centimeter per second. This is your answer. Okay. This is what your laminar flame speed. This is the basic way of calculating your laminar flame speed for a pre-mixed flame. Okay. Say engine, whatever the engine they will give, that you don't listen. This is the basic way of calculating. Okay. So now next question. When this one line kind of questions are very dangerous. Okay, and in the question only one line is there, those questions are very dangerous, and those questions are very lengthy. When the lengthy question is there, then those questions are very simple to solve. But when this one liner questions will be there, it's really difficult to solve. Okay, don't be happy that you get one line question. So that's what the case. But still it's very simple if you know the real concept, and yeah, it will be very simple. Yeah. So determine the critical radius of ignition of a stoichiometric propane air mixture at 1 atmospheric. Okay, so for this type of question the approach is very important, how you are approaching the question. Okay, so read everything carefully. Now stoichiometric condition they are giving. Okay, stoichiometry means they are giving phi is equal to 1. Okay, they are giving fuel also given C3H8 and air. Okay, okay, condition they are giving P is equal to 1 atmospheric and T is equal to 300 Kelvin. Okay. In one way Okay, one way you can write down T as TU. Okay, TU means it's an unbound case. Okay, so okay, so now what you what do you want? The critical radius for ignition. This is the important. Okay. So yeah, so this kind of question you should know. In this question, they are not telling which correct correlation you have to use. What is the temperature assumption you have to make? They are not going to tell. Okay, how the gas will be modeled? They are not going to tell. Okay, so here you have to assume many things. That's what the beauty of this type of question. If you know, only you can answer. If you don't know, you cannot answer. You see, just previously solved one very good correlation. That correlation will be applied here. Okay, net Galtis and Keck's correlation. Okay, TB is equal to T adiabatic. The bond gas temperature is same as the adiabatic flame temperature. Okay, then gas modeled using air properties. We are telling gas and air are all are same. Okay, these are some of the basic assumptions we are taking. Okay. So now fuel is given. From fuel, what are the data? You should know. These data they should actually provide. Okay, because this is a subjective question, they are not providing, but yeah, this data should be provided by them. For propane, your 5m is equal to 1.08, your bm is equal to 34.22 centimeter per second, and b2 is equal to minus 138.65 centimeter per second. Okay, now what is SLREF? bm plus b2 5 minus 5m square. Okay, just substitute and find out. Now the procedure now become now simple, because same thing whatever we done, now we are just doing it again. Okay, you see here 5, now here given 1. Sorry, yeah, I think it's given, yeah, stoichiometric it's given, yeah. So 5 is given 1, just solving. Yeah, some interruptions are there. Okay, I think up to this much I think it's clear. Okay. I just taken the propane as the fuel. 5m, bm and b2 values are taken from there. Okay, then I just find out the reference flame speed. Okay, By substituting all this value, we can find out the SLRE. As I see from the previous question, how we calculate the reference flame speed, same way we just now calculate. Okay, is 33.33 centimeter per second. Okay, this is how you just calculate your reference laminar flame speed. Okay, now here one very good assumptions we can take. Okay, so now in this question, if you see the question, determine the critical radius of ignition for a stoichiometric propane air mixture at 1 atmospheric pressure. Okay, it should be noted that 1 atmospheric pressure they are telling. Okay, that means in the previous question, if you see, they are telling the pressure is at 13.4 atmospheric, and depending upon the pressure, the temperature is also 560 Kelvin. Okay, so that means here the pressure is given at 1 atmospheric, and we assume the temperature is as what, 300 Kelvin. Okay, pressure is 1 atmospheric. Okay, that means if your P at if you see the formula of your SL reference, okay, SL is equal to this formula we can take. Okay, so T is equal to TREF, P is equal to PREF, and Y devolution nothing given, so 0. Okay, if these conditions are true, then SL is equivalent to what? SL REF is equal to 33.33 centimeter per second. Okay, so that is what the case. Okay, so when SL is equal to SLREF, when at the reference condition, if it is there, then it's SL equal to SLREF. Okay, the reference flame speed. Now we have to find out the critical radius. Okay, R critical is equal to root 6 alpha by SL. Okay, so now how you will find out alpha? K of T bar by rho U Cp. Okay, so how to find T bar? The average temperature 1 by 2 Tu plus Tb. Okay, K is the thermal conductivity. Okay, at the T bar. Okay, so now here in this question there is no born nobody tell about the what is the born temperature. Okay, so if you see, I just take one assumption here. Here what, Tb is equal to T adiabatic. Okay, that means your adiabatic flame temperature of propane is same as your bond temperature. Okay, so that means what is the adiabatic, that means you should know also what is the adiabatic flame temperature of the propane. Otherwise it's difficult to, some of the basic gases you should know, remember the adiabatic flame, like what is the adiabatic temperature of methane, acetylene, then your this propane. Okay, then hydrogen, ammonia. Okay, all these gases you should remember. So on one temperature, and this is your bond temperature. So 1 by 2 300 plus 2260 Kelvin is the adiabatic flame temperature of propane. If you solve, it's 1280 Kelvin. We assume it 1300 Kelvin, so that we can find the data from the table. Okay, 20 Kelvin having no use in the, if you are taking the unit of in Kelvin. Okay, some of the values we can find out. Okay, I told gas equal to air, we just have to take the air properties. Okay, so I just assume all this thing. This is your air properties. Thermal conductivity at T. Yes, you have to take it as at T bar everything. Okay, is equal to 0.082 watt per meter Kelvin. At the right, T bar is equal to 1300 Kelvin. Cp of T bar is equal to 1189 watt per meter Kelvin. T bar is equal to 1300 Kelvin. Rho u 1.16 kg per meter cube. T is equal to always take the density at the always take the density at the 300 Kelvin. Okay, don't take 3 bar T bar. Okay, density always on bond density is there. Okay, if you see the formula of alpha, it's rho u. Okay, means on bond. Okay, and Cp and K are in the T bar. Okay, so rho u at Tu I just taken. Okay, so alpha is equal to 0.082 divided by 1.161189. So now we have alpha 5.95 10 to the power minus 5 meters square per second. Here it's not the angle. Okay, it's the thermal diffusivity alpha. Okay, don't confuse. So means this type of question they may ask you. Okay, they will give you Tu. Okay, they will give you Tb, then ask you find out the value of thermal diffusivity alpha over. Okay, this is one question. Okay, then they will give you the fuel is propane given all the condition 5m bm b2. Okay, see this is one question to find SLREF. Okay, SLREF can be one question. Okay, then they'll ask you what is SL. If your T equal to TRA, P equal to PRA, Y dilation equal to 0. Okay, then what will be your SL? This is one question. Then they will ask you what is alpha. Okay, thermal diffusivity. If the Tu and Tb will be given, then find out alpha. Okay, that is one question. Then when all these data you have, then they will ask you what is the critical radius. Okay, R critical. Okay, that's also one more question actually. So we have alpha, and we have know also, but you should know, remember one thing, when you have to find out the critical radius of insulation, in this formula you should put in SI units. Okay, now it's in centimeter per second, you have to convert it into meter per second. Okay, R critical. Root 6. Okay, so propane's critical radius is 0.44 mm. Okay, now you just get to know that this critical radius of insulation is very negligible. Okay, so what does it mean? It means that the the Propen's effect. This is the very important conclusion you can take. Propen's effect on the mixture properties is ignored. So that's all the case. Okay. So, yeah. Try to solve one more question, short question, maybe 8.5 or 8.10 we can end this section. Okay, 8.5 I try to end. Okay, one more, one question of, yeah. This question I can solve. Okay, one question from non-premixed also we try. Okay, using the this okay, this question using the definition of volumetric flow rate Q B equal to pi r square, so that the central mass fraction YFO for a laminar jet. Okay, you should see in this this is one very well means when the question in the question laminar jet is there means given, that means you to get to know, okay, it's a not diffusional flame. Okay, so most of the time laminar jet is one term, from there we can get to know, okay, it's not a premix, it's a non-premixed flame. Okay, so jet term is the one key term, most of the question you can find. Okay, so yeah, that's all the case. Just this is a very simple question, we just quickly go through this question, and some of the more questions of chapter 9 we can cover in the next section. So this is the last question of this section. So the volumetric flow rate Q is equal to BE into pi r square. Okay, it's a very simple formula, volumetric flow rate, the exit velocity into the area. Okay, B into A. Okay, what we need to show that central line mass fraction. Okay, this question I cannot write. Center line mass fraction. Okay, IFO. Okay, so now what are the assumptions we can take? Scheme number we can take equal to 1. You should know what is scheme number also. You can search. You don't know. Constant properties. You are not taking any variable, CP or variable, all these things. Okay. Similarities. We are applying also Fick's law of diffusion. Okay. Axisymmetric flow. These are some of the very good assumptions for non-diffusional flames. Okay. 99% of the diffusional flame having this kind of assumption in this, at least in this syllabus. Okay. Okay. Axisymmetric flow. Okay, so more assumptions are there. Sixth, molecular weight of Z, and these assumption can be also one question. They will give you one condition, then 4 assumptions they will give you. Okay, and they will ask you which assumption is wrong. Okay, so it's very whatever I am now telling, all this can be a question. Okay, this is a very good type of your exit profile. Top hat. That means it will like the whatever the exit will be there, it's looking like this hat. Okay, top hat. Okay, this is a top hat exit profile. Okay. then rho equal to constant. We can see also here. Top at exit profile. Okay. Okay. This you see. Okay. This is not the case. Okay. If you can see, I actually show you wrong. That's the reason I have the doubt, so I show you. You see, this is what the your top at exit profile. Okay, it's go up. Okay, then here it's a kind of constant, and then go down. This is your right, left side is your top at, right side is your parabolic velocity profile. Okay, so that's what the top at velocity profile is. It's look like this. Okay. Okay. So now just quickly go through the solution. Okay. For schemes number is equal to 1, then your Vx is equal to 3 by 8 pi Je by mu x. These are whatever the formula I am taking. This is already given in your book. If you can see, this is already there. Okay. This is Je rho V square, rho V into A. That is kind of, you can discharge, you can tell in one way, exit discharge. Okay. Is proportional to, okay, you can tell it as some like that, what epsilon or chi or something like that, you can tell. Is proportional to r by x. Okay, so this is having very less rho. 99% of question is not there. Okay, or mostly we take 0. Okay, for center line flow or center line, for center line r is equal to 0, and mostly if r equal to 0, okay, your this chi or this whatever, you can tell c equal to 0. Okay, this term equal to 0. Okay, mostly this term is not there. Okay, 99% of case. The Vx at r equal to 0 equal to 3 by 8 pi Je by mu x. Okay, this you should remember. Okay, this is the required formula. So 3 by 8 pi rho V pi r square. Just substitute Je and mu x. Okay, mu x is this dynamic viscosity. So now you know mu equal to what? Mu is equal to mu by rho, and q is also, you know that, V into pi r square. Okay, so with these two assumptions, we already know all these things. So what we do, we just take the ratio of Vx by Ve. Okay, you see, this is your Vx, Ve, I don't write down. Okay, so take Vx by Ve. Okay, so Vx by Ve is equal to, okay, if you cancel out. It's 3 by 8 pi q by mu x. Okay, because q is your v into pi r square. Okay, and whatever mu by rho by nu is there, so that's we can convert it into nu. Okay, rho by mu is there, and v pi r square taken as q. Okay, and v get cancelled because I take the ratio of vx by ve. Okay, so now we get vx by ve. Okay, and this is the and this is for screen number is equal to 1. Okay, so finally we get to know, and this is what your YFO. Okay, this is called your YFO. Okay, okay, at r is equal to 0. Okay, is equal to 3 by, I think I made something wrong. Okay, sorry. Yeah, this is actually mu. Okay, yeah, 3 by 8 mu q by mu x. Okay. This is actually the real formula, and what is your YFO is your what? The central line mass fraction. Okay, so that's what the this formula is important. Okay, they will give you what is the value mu, discharge, dynamic viscosity, kinematic viscosity, and x. All these things they will give you. Okay, and I think they will ask about the, some confusion is there. Just I check, write down correctly or not. Okay, I actually write down incorrectly. This is actually not mu. Mu already get cancelled and converted into mu. Okay, so expression the free from mu. Okay, so only depends on your three things: function of q, mu, and x. Okay, your position in x direction, your discharge, and your kinematic viscosity. Okay, the central line mass fraction. This is very important formula. Okay, so all these values will be given, and they will ask you what is the value of y, the central line mass fraction. Okay, so set the plot. Okay, with this we can end the section. Thank you very much for attending the section. If you have any doubts, you can ask in my YouTube channel Sumit Sagar Hota. Okay, in the comment section. If you have any doubts in your lectures, you can ask in question and answer forum by NPTEL. Okay. Also solve some of the problems of the premixed laminar premixed frames in the books, and so come prepare with the non-premixed frame for the next class. We'll solve some of the problems of chapter 9 in the next class of the laminar non-premixed flame. Okay, have a good day and good night.
Nice.